Okay, what I'm going to be presenting is the results of a Monte Carlo simulation of spring-operated pressure release valves. And to actually initiate the simulation, I had to come up with a model for generating the data that was analyzed through the simulation. And the data basically arose from data that we have transferred to the CCPS PERD organization, Center for Chemical Process Safety, Process Equipment Reliability Database. The data resides in there if any of you cared to take a closer look at it, and combines our data with industry data. And to get started for the Monte Carlo simulation, I had to develop a model for the data that was representative of the data themselves, what we've experienced in testing at Savannah River. And to do that, I concentrated on the new valve database. New valves are valves that we've purchased from manufacturers, and also valves that we have rebuilt and placed within service within a few months. And the testing, basically 4 tests are conducted. The first test is the as-found condition, and 3 subsequent tests are averaged to get us the average of the last 3. But the one of primary importance is the first pop pressure. The purpose of the modeling is the new valve database is that it hasn't been out there in the field. It's of virgin condition, in other words, good shape, and it's supposed to give us an idea. I used to give us an idea as to what variability to experience within the data set. And then I place within the data an aging mechanism, which I'll show in some of the subsequent slides. But pretty much started with the training set, the new valve database. I put a failure mechanism in there. Did a Monte Carlo simulation, and I looked at a comparison of cost of inspection versus the risk that is being countered by the investment that's being made. And also present 2 case studies based on SRS data, or based on the SRS facility. And the thing about the data that resides in our database is we do know when the valves are installed, we do know when they're taken out of service, and when we conduct a test on them, we know that they've passed or failed, and we record the pop pressure. But we don't know exactly when the valves have failed. The paper that we presented this morning concentrated on a root cause analysis, engineers disassembling the valves that have failed stuck shut. Stuck shut's pretty serious, would be a pretty serious failure if in fact the valve were initiated, and that the ratio of test pressure to set pressure is 1.5. Pretty much what the purpose of this work was is to look at the maintenance program we have site-wide, and to look at a couple subsets of our site-wide system, and that's specific areas, and try to judge the risk that we're buying down by the investment in inspection. The procurement, pretty much we follow ASME guidelines and valves that are procured. The verification that we know what they are for the intended purpose. Registered in our database, fitness for service, and so forth. And also valves that are taken out of service. If they aren't the very inexpensive ones, they're repaired and placed back in the field within a certain amount of time as new valves. At Savannah River, we have, as many other places, many different fluid services, anything from air, liquid, to various gases. We have roughly, within the database that we looked at, 5,000 valves, and of various types, various set pressures, various materials of construction. Okay, the proof tests, we basically test or take the valve out of the field, deliver it to our valve shop. We don't clean it, we don't do anything with it except mount it on a testing frame, and look at what the pop pressure was. And Testing on site, roughly 1,000 valve tests per year. 9 manufacturers represent about 85% of the valve population. And it's a very diverse population of valves that we have. The maintenance intervals range anywhere from 1 to 5 years based on experience and guidelines. And we initially got into this work with the idea of actually extending the maintenance intervals to the maximum allowable under the code that we're looking at. And basically, we refine the maintenance intervals by looking at proof test data, inspection, repair results, and failure analyses and so forth. Elements of the Monte Carlo simulation. I mentioned that we do model the new valve database, valves that have not been aged. And they have various, once they're placed in service, they have various inspection intervals, different set pressures. And there's also different manufacturers. And the main purpose of this is I want to estimate the probability of failure on demand. And the valves in service actually follow a different distribution, somewhat different from the new valve database. So what I do is I developed a model from the new valve database, and then I placed that very same model in the used valve database to give a representation of the valves that I actually have in service. Okay, we're just looking at Newtonian fluid services, and Savannah River, as mentioned, the Department of Energy site in Aiken, South Carolina. Our data were uploaded into the CCPS per database and analyzed thereafter. The statistical model, I developed a model looking at the data. Now, I had a lot of different terms that I investigated for significance. I had manufacturer, I had set pressure, I had inlet size, I had fluid service. A lot of things fell out of the model, and what I essentially was left with was that the test pressure is a function of the set pressure. It makes sense. And also manufacturer terms. The manufacturer terms essentially just offset the intercept within the model that we're looking at. And the model was conducted in log space because it gave a better representation of the data, modeling it in this transform space. And once I postulated this model, did the estimation. I used the stat software product called JMP to do the estimation. I had estimates for the coefficients in the model, the beta 0, the beta 1, and different offset factors for the beta 0 term for each of the manufacturers within the model. And the error term at the far right, just random error following a normal distribution with zero mean constant standard deviation. And this shows performance of the model when fit to the used valve database. I have actual lift pressure on the x-axis, and I have predicted. And if I do have a good model, it's pretty much going to follow a straight line. Looked at this and said, yeah, I have variation about the line, but it's just natural variation. And I was able to estimate the unknown coefficients within the model. Well, to conduct the simulation, what I do is I take this. I took this model, I placed it in the used valve database, and these terms, like the beta 0 term, I have an estimate here. I say it's 0.108 plus or minus a certain standard error. Well, I simulated. I said, let's assume beta 0 follows a normal distribution with this mean and representative standard deviation. The same thing for the slope term, and the two deviates are correlated, and I built that into the simulation. To show an illustration of what it might look like, here I took a particular valve, set pressure I think was 350 pounds for the set pressure. I generated data out to 6 years, but I built in a failure or a deterioration mode into this model that what we see in equation 2 is the model that I fit to the data, and down in model 3 I actually put how the valve deteriorates over time. I have the ratio. Here I'm assuming a 3% per year deterioration rate, the time in years, and I took it to be a function of the set pressure. So I'm not looking at kind of like accumulated percentages here like you do in a money market account or savings account or a CD, but a constant set pressure times years, a constant ratio times years times the set pressure. And this illustration here, I just took one data set. I generated millions of these in doing the simulation. This is just a plot of one of them. And I just wanted to show that I'm getting a reasonable representation of perhaps corrosion deterioration over a certain period of time, where in fact the deterioration rate was assumed to be 3% a year. Now the simulation, I don't take it to be fixed at 3%. I do it for 1%, 2%, 3%. I can set it to be whatever I like within the simulation, and then look at the performance of the preventative maintenance program that we have. Okay, the bottom section here, the bottom bullet, Monte Carlo simulation that I conducted, what I call PM Freak Zero is the preventive maintenance program that we have in effect at Savannah River. Okay. At first I said, what would happen if I shorten all of the maintenance intervals by 1 year? That is the PM Freak Zero -1. And then I said, well, what would happen if I extended the maintenance intervals by 1 year and then subsequently by 2 years? What kind of performance would I expect? And the reason for doing this is with this failure mechanism that I built into the model, I know what to expect at certain points in time, whereas in actuality, when a valve is tested at the end of the maintenance interval, it could have failed on day 1, or it could have failed 2 days later, or it could have failed just before I took it out of service. I basically transform the data back into the original metric of test pressure. This is the model I'm dealing with the deterioration rate showing over on the right-hand side. And the whole purpose, estimate probabilities of failure on demand. When valves are removed from service, maintenance interval tested, and we replace them with new valves. Failed dangerous mode, ratio of 1.5 or greater. In other words, stuck shut, very serious situation. And but within the model, I said, well, perhaps I'm going to be dealing with I picked a rate of 1.3 instead of 1.5 as being a leading indicator that it's headed toward a failure rate of 1.5. And the reason I did this, I wanted to be analyzing a little more data. I picked up a little more data in the simulation, and this would be a predicator to perhaps the valve deteriorating, and I'd want to pick it up. Define risk, probability of failure on demand times consequence, and I generated various risk curves. But before I did that, I said, okay, preventative maintenance Freak Zero. What's my average number of inspections per year? Converted that into tests per month. Far right-hand column, I have the number of valves within each of these intervals, and so forth. And the program that we have, the average inspection time is 3.7 years, and that comes out to be about 21.2 tests per month for our population. What I have here is a plot of risk versus the cost of maintenance. And pretty much at 21 valves tested per month, 21's on the x-axis, I'd come up and see what curve would intersect, and it looks like from this curve that I'm getting protection for a 4 to 5% deterioration rate per year. And if I were inspecting 10 valves per month, I would venture a guess that I'm buying protection up to deterioration rate of 1% a year. Being a statistician, I like to calculate confidence intervals for things, so I generated upper 95% confidence intervals for the risk curves. And at 21 valves tested per month, 95% upper limit for it would be buying protection for a 3 to 4% protection rate per year. But the thing here is we have a preventive maintenance program. What is its effectiveness? What protection am I buying for the investment that I'm making? And the simulation helped me to establish those values. We looked at a couple cases, and one is consequence $500,000. The other was consequence $2 million, and these were subsets of the population of valves that we have out there. In other words, a part of the business that we have at Savannah River, or a particular process. Details about it, I don't need to go into that right now with the remaining time that I have. But the first step in doing this is to look at the average number of tests per year, convert that into tests per month. The maintenance program that I have is basically tuned to, bottom line, 0.86 tests per month, or roughly 9 tests every 10 months. So look on this curve where I have a 0.86, and it looks like I'm buying protection up into about 3 to 4% deterioration rate. And the whole idea, as I've mentioned already, is we don't know exactly when these valves failed unless we disassemble them, got an expert to spend a lot of time with them and try to determine when they failed by judgment. Or the other thing is to build a model and try to evaluate the preventive maintenance program we have through modeling and Monte Carlo simulation, but we just can't do that from nothing. We have to develop a training model. And the training model came from the CCPS data that we have available. Looked at a case of larger consequence. First thing to do is to try to determine average number of tests per month under the current maintenance program. And it's roughly 2 tests per month, buying protection on up to 3.25%. So where we were last year, we analyzed a lot of the data, the inspection data, POP data that we have, and we used the maintenance interval. And or folks in the past used the maintenance interval as the time to failure. And what we found last year in simulations that I ran was we could be underestimating the risk by a factor up to 100%. And because of that, we started in looking at ways that we could evaluate performance of valves without knowing the actual failure date. And one was this morning's paper, the root cause analyses with experts determining when the valves fail, or using a Monte Carlo simulation and building a model that generates data that's representative and realistic, and using that to judge the performance of our maintenance system. And the question is, can we shorten the maintenance intervals, or could we expand the maintenance intervals within their allowable range? And this is a tool that we have available that would be able to do that.